Welcome back. Today I am here with theorem 1.5 of chapter 1 real numbers NCERT maths textbook class 10. What does theorem 1.5 say? Let's begin. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are coprime and the prime factorization of q is form 2 power n into 5 power m, where n, m are non-negative integers. Here I have explained you theorem 1.5. If we have a rational number of the form p by q, like 3 upon 10, and the prime factorization of q is of the form 2 power n into 5 power m, where n, m are non-negative integers. It means the powers cannot be minus 3, minus 2, such powers are not allowed. Then does p upon q have a terminating decimal expansion? Here the entire focus is on q. Q means denominator. The denominator can be of the form, in short I will say that the denominator q should be of the form 10, 100, 1000. If they are of the form 10, 100, 1000, then the prime factorization, what is the prime factorization of 10? It is 2 into 5. Now of 100, it's in the power of 2 and power of 5. Of 1000, again the power of 2 and power of 5. So when the denominator is of the form 2 power n and 5 power m, means it is in the form 10. 10, 100 multiples of 10. Right? So our focus will be on the denominator. If it is in the multiple of 10, then it will have a terminating decimal expansion. Let me again explain you with more examples. Theorem 1.6 follows from theorem 1.5. Any rational number of the form a by b, where b is a power of 10, will have a terminating decimal expansion. So it seems to make sense to convert a rational number in the form p by q, where q is of the form 2 power n, 5 power n, to an equivalent rational number of the form a by b, where b is the power of 10. Now we are going to convert the q in the form of power of 10. This I will explain you with more examples. Examples of theorem 1.6. Here I have taken a simple example 3 upon 8. Here you have to focus only on denominator. What is the denominator? 8. What is the prime factorization of 8? 2 into 2 into 2. That is 2 cubed. Now it is not in the form of 10. We have to convert it in the form of multiples of 10. So what can we do? The same we have to take in the power 3, but in the base there will be 5, because 2 5s are 10. So whatever is 2 power 3, you have to take into 5 power 3 in the denominator. So 2 into 5, 10, power should be equal. So 10 power 3. Now whatever we multiply in the denominator, the same number should be multiplied in the numerator. That is the rule of equivalent fractions. So we are converting it into equivalent fraction. So here again in the numerator we will multiply by same 5 power 3. Now 5 power 3 is 125, and 125 into 3 is 375. So 375 upon 10 cubed. So 10 cubed means the 1000, and the decimal place will be before 3 digits from the this right side. The next example 13 upon 125. is equal to 13 upon 5 cubed. What is the prime factorization of 125? 5 into 5 into 5. So that is 5 cubed, which I already mentioned before also in the above example, that 125 is equal to 5 cubed. Now here there is a reverse order. 5 is there and 2 is not available. So we will multiply by 2 cubed. The same mind well, the power should be same. So 2 cubed in the denominator. To convert it into equivalent fraction, we have to multiply by 2 cubed in the numerator. So 2 cubed into 13 is 104, because 2 2s are 4, 4 2s are 8, 2 cubed is 8, 8 into 13 is 104. And in the denominator, again you get 10 cubed. So 10 cubed is 1000, 104 upon 1000 is equal to 0.104. Because 3 zeros means after decimal there will be 3 numbers. Now move to the last example, 7 upon 80. Here, what is the prime factorization of 80? 2 power 4 into 5. This is the prime factorization of 80. 2 2s are 4, 2s are 8, 2s are 16, and 16 5s are 80. But now, what I told, the power should be same. We are already having 1 5 and we require 3 more 5s. Then it will become 5 power 4. So, after multiplying by 5 cubed, mind well, 1 5 is there, 3 more 5s are needed. So we are going to multiply by 5 cubed. So 2 power 4 into 5 cubed. If we multiply by 5 cubed in the denominator, we need to multiply by 5 cubed in the numerator. Now let's go to denominator. 1 5 is there. We are multiplying by 5 cubed. So 5 into 5 cubed is 5 power 4. Now both the powers have become same. 2 power 4 and 5 power 4. They have become equal. So you get 2 5s are 10 and power is 4. 875 upon 10 power 4 is equal to 0.0875, because it is 10,000. Now here's the statement of theorem 1.6. Before I explained you theorem 1.6, and now I am putting the statement. Let x is equal to p upon q be a rational number such that the prime factorization of q. You remember in the previous slide we saw 3 examples where we did the prime factorization of denominator. So denominator means q. Prime factorization of q is of the form 2 power n 5 power m. Even remember that the powers were not equal, we converted them into equal powers. So where n and m are non-negative integers, then x has a decimal expansion which terminates. Here I have taken example. Without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating decimal expansion. Here I have taken the examples of terminating decimal expansion from NCERT book exercise. These 2 examples which you are seeing on the screen are of only terminating decimal expansion. The first one is 23 upon 8. As you can see, 23 upon 8, the denominator is 8. The prime factorization of 8 is 2 cubed into 5 power 0. 5 power 0 is 1. Denominator 8 is 2 cubed into 5 power 0, which is in the form 2 power n into 5 power n. Why? Because 5's power is 0. Therefore, 23 upon 8 is the terminating decimal expansion. One more example I have taken, 35 upon 50. Sometimes the prime factorization is not easy. You cannot do it orally. Like for 8, you can do it orally. 2 2s are 4 2s are 8. But here for 50, if you don't know to do orally, doesn't matter. Make a column and start doing a prime factorization. 2 25s are 50, 5 5s are 25, 5 1s are 5. So how the denominator goes, I have marked with arrow. There is 1, 2, so 2 power 1. There are 2 5s, so 5 squared. 35 upon 2 power 1 into 5 squared. Now the denominator 50 is of the form 2 power m into 5 power n. So this 35 upon 50 will definitely have a terminating decimal expansion. Here mind well, the denominator is only of the form 2 power m and 5 power n. no other number is introduced. Like if you are seeing the red arrow, I have specially marked that it is of the form 2 power m and 5 power n. If there was multiplied by just for example, let us think that if it had been multiplied by 3, if 2 into 5 into 3, then it would not have been a terminating decimal expansion. Only 2 and 5 are required. Explanation of Theorem 1.7. In chapter 1 of your class 9th textbook, you have already done the division of 1 upon 7. This division, you remember, if you remember how it goes, it's already on the screen. Notice that the denominator here, 7, is clearly not of the form 2 power n, 5 power m. Know that 1 upon 7 will not have a terminating decimal expansion, and 0 will not show up as a remainder, and the remainders will start repeating after a certain stage. So we will have a block of digits, namely 1, 4, 2, 8, 5, 7, repeating in the quotient of 1 upon 7. Now, you see the denominator. What is in the denominator? 7. What will be the prime factorization of 7? 7 itself. It means it is not of the form 2 power m and 5 power n. 2 and 5 are nowhere seen in the prime factorization of 7. So now here goes the division. Even if you see the division part, you see that there won't be 0. I have depicted everything with an arrow. The remainders are 3, 2, 6, 4, 5, 1, and again the 3 is repeating. So one block is there. After one block, the same numbers will start repeating. The block is, you see the block in the quotient, not in the remainder. The block is 0.142857. So this is the block. This block will repeat again after 7. Again 142857, 142857, like that. The arrow are showing that you won't get 0 anywhere. Whenever you start dividing, some another number will come and you will continue dividing, but you won't end up with 0. And after last, you see, after 1, 3 is repeating. Once the 3 starts repeating, you have to stop the division, because you now understand that again the same numbers are going to repeat. So what is the block? The block is 142857. So this is non-terminating decimal expansion. So now we will make the statement of theorem 1.7. Let x is equal to p upon q, the same as theorem 1.6. The starting is same. Let x is equal to p upon q, where p and q are co-prime numbers, be a rational number such that the prime factorization of q is not of the form 2 power n, 5 power m, where n and m are non-negative. This is repeating, same things are repeating. N and m are non-negative integers. Then x has a decimal expansion. This statement is also same, but last, which is non-terminating repeating. It's non-terminating repeating, means recurring. Here, co-prime numbers, I have to say p and q are co-prime numbers, means it's in the standard form. You cannot divide it further. That's all. The last line is very important. X has a decimal expansion which is non-terminating repeating. Repeating means the block is again and again repeating. As we saw in 1 upon 7, the block was repeating and you did not get remainder 0. It means it was non-terminating. Without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. This, I have already taken 2 examples of terminating decimal expansion from your exercise of the NCERT book. Now I am taking 2 examples of non-terminating decimal expansion. The first example is 125 upon 441. 441 is a larger number, so we better do the prime factorization. When we carry out the prime factorization, what we are getting? We are getting 3 squared and 7 squared, which I have shown with an arrow. We have to only focus on the denominator. Now in the denominator, you are seeing that it is not of the form 2 power n and 5 power n. What its form is, you see, 3 and 7. They are the powers of 3 and 7, not 2 and 5. Therefore, 125 upon 441 is not terminating decimal, not terminating repeating decimal. Understand that it will repeat, the block will repeat, but it is non-terminating. So I have even highlighted, you have to write non-terminating. How you came to know that it is non-terminating? You go to the denominator. The denominator has powers of 3 and 7. Nowhere you can see 2 and 5. That is why it is non-terminating. The second example which I have taken, 77 upon 210. First you convert it into co-prime numbers, which we have already seen in the statement. So I have converted into co-prime numbers by dividing it by 7. What means co-prime numbers? The standard form. It means now you cannot, 11 upon 30 once you get, then you cannot divide further. 77 upon 210 has a common factor 7. So when you are dividing by a common factor, you get a standard form 11 upon 30. Now focus on the denominator 30. Next step, do prime factorization of 30. Next step, write it in the product form, which I have already shown in by an arrow. Here in the product, you are having 2 power 1, 3 power 1 and 5 power 1. I have shown with that arrow that 3 power 1 is there, which is not required. If it was a terminating decimal expansion, then 3 power 1 was not required. It would have been of the form 2 power m and 5 power n. So here the 3 is extra number, which will show that it is the non-terminating repeating decimal expansion. So see, I have highlighted 30 is not of the form 2 power m and 5 power n. Therefore 11 upon 30 is non-terminating repeating decimal expansion. So children, if you like our video, please like, share and subscribe it. Thank you.